This is a production of the Chemical Education Material Study.
A lightning flash comes from ionization of the atmosphere. A Tesla coil produces a similar, more controlled effect in laboratories. Flames also ionize gases, as shown by their conductivity of the Tesla coil spark. That's why you should stay away from flames surrounding electric wires. Let's explore the energy required to ionize a gas. Here's a piece of metallic sodium in a beaker. In this container, we can warm the sodium and at the same time surround it with chlorine gas. First, the sodium melts. The bubbles show chlorine gas flowing toward the beaker. Then, as the sodium vaporizes, a reaction begins. In this reaction between sodium gas and chlorine gas, each sodium atom loses an electron to a chlorine atom, and the ionic substance sodium chloride is produced. In the reaction, a 3s valence electron from each sodium atom has been transferred to a chlorine atom, as shown on these orbital charts. Neon is the element just preceding sodium in the periodic table. It has only one electron less than sodium. Let's see if neon reacts with chlorine. First, the beaker is filled with neon. Then it is heated, just as we heated the sodium. Moisture condenses on the outside of the beaker at first, but it disappears as the beaker warms. Chlorine gas is added. You can see it mixing with the hot neon gas. Yet, no reaction can be detected. Neon is inert, in contrast to sodium. Unlike sodium, neon did not ionize. One of the factors that determines the difference in reactivity between sodium and neon is a difference in their ionization energies. In this film, we shall see how ionization energy is measured and how it varies. To show one way in which ionization energy can be measured, let's look again at metallic sodium. The ionization energy is the energy required to remove an electron from an isolated atom. And in solid sodium, the atoms are not isolated. However, when sodium is melted and vaporized, individual isolated sodium atoms are formed in the gas phase. This is a representation of an isolated neutral gaseous sodium atom. When a gaseous sodium atom absorbs enough energy, for example from a photon, the single valence electron may be ejected, leaving a gaseous sodium ion. Electron ejection occurs when we measure ionization energy. Ionization energy, then, is the minimum energy needed to remove an electron from a gaseous atom. The energy needed to ionize the atom can be delivered to the atom in the form of light, heat, or electron bombardment. Here is an experimental device for measuring ionization energy. It consists of a vacuum pump, several reservoir bulbs of gases, and an apparatus in which electrical conductivity of gases can be measured. Ionization produces an electron and a positive ion from a neutral atom. Thus, the electrical conductivity of any gas present will show a sharp increase when ionization occurs. This cell is placed in an oven and contains 2 electrodes so that the electrical conductivity of any gas between them can be measured. The wires through the cell walls connect the electrodes to a battery so that an electrical current flows when ions are formed in the gas. For this experiment, the source of energy used to ionize the gas will be light from a mercury lamp. The light is directed by a series of mirrors through a quartz prism, which will separate the light into a sequence of energies or colors. When the light enters the cell, it may be absorbed by gas atoms to form ions. All the light that enters the cell must pass through this slit, which admits only a single color at a time. Now, let's cover the lamp, turn it on, and see how the instrument works. The light passes through the prism, which separates it into different colors. Each color of light has a characteristic frequency which determines the energy. The slit admits only one particular frequency at a time to the cell. We have covered the instrument to keep out external light. The micrometer head, which controls the quartz prism, allows us to select a single frequency, or color, to pass out through the slit and enter the cell. This green light has a frequency of about 7 times 10 to the 14th cycles per second. As the color changes from green through yellow toward red, the frequency decreases to about 5 times 10 to the 14th cycles per second. The energy of the light becomes correspondingly lower. Moving the prism the other way, we go toward violet. And then, continuing to still higher frequency settings, ultraviolet light comes from the instrument. But our eyes don't respond to it. To find the energy of any particular color of light, multiply its frequency, nu, by the conversion factor H, Planck's constant. Now, let's proceed with the experiment. There's sodium here in the sidearm of the cell. When the surrounding oven gets hot, gaseous sodium will fill the cell. We must make our measurements on pure gaseous sodium, so we evacuate the cell. This gauge shows the pressure in the cell. For our experiment, the pressure must be less than 1 micron, less than 1/1,000,000th of an atmosphere. Now we have a good vacuum, so we'll turn on the oven and heat the sealed-off cell. The sodium melts and starts vaporizing to gaseous sodium. The energy of the light, which shines through the oven and cell windows and into the gas, will vary. We begin with low-energy red light. Watch the meter while we slowly increase the frequency of light entering the sample. Yellow, green, blue, ultraviolet. There, the meter reading becomes large, indicating a large increase in the conductivity of the gas. The high-energy ultraviolet light has ionized the sodium. Let's go back and measure the lowest frequency which causes ionization. We will increase the frequency slowly and watch the meter more carefully this time. There, the conductivity rises rapidly. The micrometer reading corresponds to an ultraviolet frequency of 12.4 times 10 to the 14th cycles per second. This diagram represents what happened. The high-energy light photons ionized the sodium atoms. The released electrons go to the positive electrode, and the sodium ions move to the negative electrode. Electric currents flow. The gas has become conductive. Here is a representation of the process at the atomic level. A sodium atom absorbs a photon and almost immediately ejects an electron. The resulting charged particles then move under the influence of the electrodes. This process is called photoionization. A sodium gas atom plus a photon gives a sodium gas ion plus 1 electron. We use this equation to calculate the ionization energy of sodium. We have determined that nu equals 12.4 times 10 to the 14th cycles per second in this equation. Now, multiplying by the conversion factor H, 9.53 times 10 to the minus 14 kilocalorie seconds per mole, we find that the ionization energy of sodium is 118 kilocalories per mole. Considering the simple apparatus used, this value compares well with the accepted value of 118.4 kilocalories per mole, or 495.4 kilojoules per mole. You have seen that one of the ways to measure ionization energies is to use photons to provide the energy for ionization. Another way is to bombard with fast-moving electrons. This alternate method can readily give much higher energies and permits us to check our earlier results. This apparatus will generate electrons and make them move very rapidly by strong electrical forces that can be easily controlled. Here is a diagram of the apparatus. Again, a circuit of 2 electrodes with a battery and meter will be used to detect current flow, hence the presence of ions. This filament inside the cell is connected to a battery. When the filament gets hot, it emits electrons from its surface. This is a metal screen through which most of the electrons can pass. It is called a grid. The grid is connected to a source of positive voltage which attracts the negative electrons. The higher the positive voltage on the grid, the faster the electrons accelerate toward the grid. So, as the accelerating voltage is increased, the electrons are given more and more energy. This is very similar to the previous experiment, except that instead of photons, electrons pass through the cell. When the bombarding electrons acquire high enough energy, their collisions with gaseous sodium atoms should produce ions, and the conductivity of the cell should rise and be shown by the meter on the lower left. Now let's proceed with the experiment. Once again, all other gases must be removed from the cell. Again, we'll use the vacuum pumps. The gauge shows that there is a good vacuum. When the cell reaches a temperature sufficient to vaporize the sodium, we can begin. Now we're all set. As the accelerating voltage increases, the bombarding electrons carry more and more energy. Very little current flows through the sodium vapor, as you can see by the meter on the left, until the voltage reaches a critical value. Then the current shows a rapid rise. Let's repeat, this time carefully reading the accelerating voltage at which a large increase in the current occurs. These random fluctuations are not meaningful. There, ions are now being produced. The voltmeter reads 5 volts. On the atomic level, an electron with sufficient energy ionizes a sodium atom, producing a second electron and a positive sodium ion. As before, the sodium ion is attracted to the negative electrode at the top, and electrons are attracted to the positive electrode at the bottom. The process of exciting a sodium atom so it can eject a 3s electron is represented by this equation. Energy comes from the bombarding electron. The ionization energy of sodium can be calculated from the measured accelerating voltage of 5 volts. An energy of 5 electron volts was given to each electron. We can change the units to kilocalories by multiplying by the conversion factor 23.1. Thus, we obtain about 115 kilocalories per mole with an uncertainty of about plus or minus 10. In kilojoules per mole, this would be 481 plus or minus 40 kilojoules per mole. This is in good agreement, within experimental uncertainty, with the value determined by the photoionization method, 118 kilocalories per mole. Now, sodium is a highly reactive element. Let's use this electron bombardment method to measure the ionization energies of some of the highly unreactive noble gases. Here are helium, argon, xenon, 3 of the noble gases. This tubing can fill our cell with any one of the 3 gases. Let's start with helium. The cell is already empty, so we can now admit our sample. Helium is a gas at room temperature, so there's no need to heat it. It takes a voltage considerably higher than that for sodium to cause the ionization process to begin. Now watch the meter on the left. There. This sudden large rise indicates that ionization has occurred. The reading is about 25 volts, nearly 5 times the value for sodium. This value is in reasonable agreement with the value we find in a reference book, 24.6 volts. This more precise value is an ionization energy of 567 kilocalories per mole, more than 2,000 kilojoules per mole. Now the next noble gas, argon. The helium has been pumped out of the cell and argon added. We proceed as before. There we go. Ionization begins. The reading is about 16.5 volts when ionization occurs. The accepted value is 15.8 volts, which corresponds to 363 kilocalories per mole, about 1,500 kilojoules per mole. Now a third noble gas, xenon. The argon has been removed, so xenon can be added to the empty cell. Now we're ready to measure its ionization energy. The reading is about 12.5 volts this time. The accepted value is 12.1 volts, which corresponds to 280 kilocalories per mole. From a reference book, we've added the ionization energies of krypton and neon to our list. The ionization energies are all high. Reactive sodium was only 118. Unreactive neon is 497 kilocalories per mole. Plotting these ionization energies against atomic number will show any trends as related to the periodic table. Helium, with atomic number 2, has an ionization energy of 567 kilocalories per mole. It goes here. When we plot the rest of the noble gas data, we see that the ionization energies of the noble gases decrease with increasing atomic number. The ionization energy of the alkali metals can be added to the plot. Lithium, sodium, and the others. The ionization energies of the reactive alkali metals are all much lower than those of the unreactive noble gases and show little decrease as atomic number increases. With this same chart, we can show the ionization energies of most of the elements. Within a given row of the periodic table, the ionization energy tends to rise as the atomic number increases. This characteristic trend is repeated in each row. We find the same kind of cycling in the chemical properties of the families of elements. Variation in ionization energy is one reason for the existence of these families. Ionization energy, then, is the minimum energy needed to remove an electron from a gaseous atom. We have explored two measurement techniques: photoionization, electron bombardment. We have compared the ionization energies of the noble gases to those of the alkali metals. We have indicated how, across each row of the periodic table, the ionization energies tend to increase, forming a pattern which not only helps us explain the regular trend in chemistry from element to element, but it helps us understand the very existence of the periodic table. For example, iron corrodes as it loses electrons to oxygen. This is consistent with the low ionization energy of iron compared to that of oxygen. Corrosion is prevented if a layer of paint stops the electron transfer by keeping the iron from contact with oxygen. This is only one of many chemical reactions that can be understood in terms of ionization energies.